Hello, this is Jonathan Masiha, and I am recording my demonstration for exam number one. So for the first question, we are supposed to correct a question that we got wrong on the exam. For exam number one, I missed part C of this question, and that was the only one I missed. Uh, Real quick, I will read the question to you. It says the graph of the function f and g is shown below. The function f is defined on the interval -infinity to -3 and -3 to infinity. And the function g is defined on -infinity to -3 and -3 to infinity. So this is the graph of f, and this is the graph of g. And so these were a few of the parts of the question. I missed part C. It says determine where f over g is continuous. And so right here, you can see this is the part that I got wrong. I said that it was -infinity to the -3, -3 to 4, and then 4 to infinity. And so while this is right, one mistake that I had was I neglected the discontinuity at x equals 8. So as you can see from the graph, the reason I said that there's a discontinuity right here at -3 and then one at 4 is that, as you can see on the graph of g, there is an undefined value right here at -3 at x equals -3. There's actually also one on the graph of f. And while there is none at 4 on the graph of f, there is one at 4 on the graph of g, as you see this jump discontinuity right here. So therefore, because of these two discontinuities at -3 and 4, there is a break right here. So my mistake, however, was not including it at x equals 8. Now, the reason for this is because of theorem 1.5.1e, which states if f and g are continuous at a and c is a constant, then the function f over g is also continuous at a, provided that g of a does not equal 0, because as you can see right here, g is in the denominator, and that would make that undefined. So g of a could not equal 0. So we have to look at the graph of g and see when it equals 0. And so you see right here, it crosses the x-axis at 8. And because of that, this is where g equals 0. That makes it discontinuous right here at this value. And because of that, you must include a break in the interval at x equals 8. And so while what I had was correct, I did not include this part, which is that 4 goes to 8, and then it's broken up, and then 8 goes to infinity. So you can see right here, this is the full correct answer with the 3 discontinuities at -3, 4, and 8. And so moving on to the second question, it states, let f be a function with the following property, x over x squared minus 2x minus 3. And then that is less than or equal to f of x, which is less than or equal to 3 times 4 to the x minus 3 over 4x minus 12. And so that is when x is greater than 3. So use squeeze theorem to compute the limit as x approaches 3 from the right side of x minus 3 times f of x. So right here, you see I just wrote this out as we are evaluating this. And so your first step right here is going to be multiplying x minus 3 to both sides, as you do when doing squeeze theorem problems. So you distribute this to both sides, and that will give you this right here, x times x minus 3 on the top, and then this times x minus 3 on the top. The denominators will stay the same here. And so once you factor that out, or actually before you do that, you're gonna factor the bottom. And while you, after doing this, you can see this can be broken up into x minus 3 and x plus 1. And then on this side, if you take out the 4, that leaves you with x minus 3. And so now we have x minus 3 on the denominator of both sides of this. And now you can cross them off right here on the top and the bottom, and then do the same on this side. And after doing that, that should leave you with x over x plus 1 is less than or equal to f of x, which is less than or equal to 3 times 4 to the x minus 3 all over 4. And so now that you have this, and that you've rewritten these equations, you are now able to calculate the limit as x approaches 3. And so as you see right here, with this function, you're going to plug in 3, and that will give you 3 over 3 plus 1, which is 3/4. And then right here, and that is because it's less than or equal to, that is from the left side. What we want was the right side, which you can see right here as x approaches 3. You plug in 3 right here, that gives you 3 times 4 to the 3 minus 3 all over 4. And a 0th power will give you 1, making that 3 times 1 over 4, and that is 3/4. So now you see that the limit from the right side is 3/4, the limit from the left side is 3/4, and that does mean that the overall limit for this function is 3 over 4, which was found using squeeze theorem. So that is it for the second problem. Now moving on to problem number 3, which is a multi-step problem. It starts off by saying the derivative of a function f at a can be computed by computing the limit as h approaches 0 of f of a plus f of a all over h. Now, if the limit is a finite number, then it is differentiable at a. However, what happens if the function f is piecewise? And how do you compute its derivative? So to start, we will be working with this function right here, this piecewise function. It says f of x equals x plus 1 if x is less than 2, and then it equals half times x minus 1 squared plus 5 over 2 if if x is greater than or equal to 2. And so turns out that the derivative will also be a piecewise function. So starting off right here in question A, this function is continuous everywhere, except there might be a problem at x equals 2. First, confirm f is continuous at x equals 2 by checking the 3 conditions of continuity. So the 3 conditions of continuity are right here. It says f of a is defined. Number 2, the limit as x approaches a of f of x exists. 3, the limit as x approaches a of f of x equals f of a. So let's start off with the first one right here, and that is that f of a is defined. So you can take each part of the equation of this piecewise function. First, you take the x plus 1, and you see if it is defined. So x plus 1 is just a linear function, and that makes it defined on the interval -infinity to infinity. The second function, as you can see here, x minus 1 squared, this is going to be a parabolic function. So parabolic functions are also defined on the interval -infinity to infinity. Because of this, you know, therefore, that f of a must be defined, as it is always defined due to these 2 equations. So you can check off part 1 of the conditions of continuity. Moving on to part 2, the limit as x approaches a of f of x exists. So basically, the limit as x approaches a from the left must equal the limit as x approaches a from the right. If that happens, then we know that the limit exists. So what we're going to do here is, you know that the function is x plus 1 when it is less than 2, when x is less than 2. That means that this will be analyzed as the left side. And then this is the function when it's greater than 2. So this will be analyzed as the right side of the function. So starting with the left side, if you plug in 2 right here, you get 2 plus 1. And then you can see that the limit as x approaches 2 from the left is 3. Now on this side from the right, if you plug in 2 here, you'd get 2 minus 1 squared, which is 1 squared, so half, plus 5 halves, and that gives you 6 halves, which is equal to 3. So the limit as x approaches a from the right is 3. The limit as x approaches as x approaches 2 from the right and from the left, they're both 3. So therefore the limit does exist at x equals 3. And the second condition of continuity is also satisfied. So moving on to the third condition of continuity, which is the limit as x approaches a of f of x equals f of a. We know from over here that the limit as x approaches a of f of x is 3. We just calculated this by looking at it from the left and the right side, and knowing that the entire limit is x equals, or the entire limit exists at x equals 3. We know this. And so all we need to do to check this condition is find f of a. And so when you plug in 2 right there, because a is 2, you get 2 plus 1 equals 3. For the first equation, you plug it in, you get the same thing. It equals 3 for the other equation. So you know that f of a does in fact equal 3 for both parts of the piecewise, and you know the limit is at 3. Therefore, the limit as x approaches a of f of x does in fact equal f of a. And so that is part A, and you can see that all 3 conditions of continuity are in fact satisfied. So moving on to part B, what is the derivative of f? We will answer this in parts. For this part, let's focus on when a is less than 2. What is f prime a, or the derivative of f? Since a is less than 2, our function f looks like f of x equals x plus 1 when x is less than 2. Therefore, the limit as h approaches 0 of f of a plus f of a over h equals the limit as h approaches 0 of a plus h plus 1 minus a plus 1 all over h. So compute this limit, and this will tell you what f prime a equals when a is less than 2. So what we're going to do is, because the question actually already plugs this in for us, all we have to do is deal with breaking this down. So you see the limit as h approaches 0 equals this, a plus h plus 1 minus a plus 1. And so what we're going to do here is add these up when you plug in 2, because we are evaluating this at 2. So plugging in 2 is going to give you 2 plus h plus 1, so h plus 3. And then a plus 1, which is 2 plus 1, so another 3. That'll give you h plus 3 minus 3, as you can see right here, all over h. These will cancel out, and that leaves you with h over h, which is just 1. And so you can see that the derivative when it is less than 2 is equal to 1. Now, moving on to part C, let's focus on a is greater than 2. So what is f prime a? Since a is greater than 2, our function f looks like f of x equals half times x minus 1 squared plus 5 over 2 when x is greater than 2. Therefore, the limit as h approaches 0 of f of a plus h minus f of a all over h equals the limit as h approaches 0 of half times a plus h minus 1 squared plus 5 over 2 minus half times a minus 1 squared plus 5 over 2 all over h. Compute this limit, and this will tell you what f prime a equals when a is less than 2. So this is what we are going to be evaluating right here. And so the first step will be plugging in the 2 for the a. As we know it is, we are evaluating it at when a is greater than or equal to 2. So that'll give you the same thing right here in h plus 3. And then when you plug this in here, this will give you an actual number. So plugging in 2 will give you 1, and 1 squared is 1 times half is half plus 5 halves again. That's going to give you 3. So this is going to end up just being minus 3 right here. And then after plugging this in, h plus 3, you can now multiply that out, and that'll give you half times h squared plus 2h plus 1 plus 5 halves and then minus 3. So now we can kind of condense this a little bit. I multiplied the half out and made it h squared over 2, got rid of the 2 in front of the h, and then the 1 became a half. And now that you've done this, you can combine all 3 of these terms. So that would be half plus 5 halves, which is 3. And then minus 3, that all actually cancels out and leaves you with just this h squared over 2 plus h. And again, that is still all over h. So now, breaking this down even more, you can take an h out of the top, and that gives you h times h over 2 plus 1 all over h. You can now cancel out these h's, and now that leaves you with the limit as h approaches 0 of h over 2 plus 1. And now finally, you can plug in 0 here to give a u is 0/2, which just equals 0, plus 1, and that equals 1. So now you notice that the derivative from the left side is 1 and from the right side is 1. So now moving on to part D. Now, what is the derivative of f at a equals to, as I just mentioned? Because the form of f will differ depending on if we are on the left side of 2 or the right side of 2, computing the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h will require we compute this as two one-sided limits. So in other words, compute the limit as h approaches 0 from the right of f of 2 plus h minus f of 2 over h, and the limit as h approaches 0 from the left of f of 2 plus h minus f of 2 all over h. When h is greater than 0, the number 2 plus h will be bigger than 2. So this means f of 2 plus h equals half times 2 plus h minus 1 squared plus 5/2. Therefore, the limit as h approaches 0 from the right of f of 2 plus h minus f of 2 all over h equals half times 2 plus h minus 1 squared plus 5/2 minus 3/h. So compute this limit. And that's kind of what we did in the steps in the last problem. So now we're going to be computing this limit right here. Again, this is actually, this is now 2 minus 1. So this is going to give us h plus 1, which we're now going to factor out. That gives you h squared plus 2h plus 1. And now the same thing right here as we did in the last problem, 5/2 minus 3. If we combine those, that's going to leave you with a half. So that's going to be minus half right there. And so now after you multiply this out, this is what you're left with right here, which is the limit as h approaches 0 from the right of half times h squared plus 2h plus 1. And then that's minus half all over h. So we're kind of going to do the same thing as we did in the last problem, and that is distribute out that half. That'll leave you with h squared over 2 plus h plus half. And then again, minus half. These are going to cancel out. And that will leave you with this same thing right here, where you take out the h, cancel them out in the numerator and the denominator. And then that's going to leave you again with h over 2 plus 1. Plugging the 0 in gives you a 1. And so that now shows you what the derivative is at a equals 2. But now we're going to analyze this again when h is less than 0. So the number 2 plus h again, this time it's going to be smaller than 2. So this means f of 2 plus h equals 2 plus h plus 1. Therefore, the limit as h approaches 0 from the left of 2 plus h minus f of 2 over h equals the limit as h approaches 0 from the left of 2 plus h plus 1 minus 2 all over h. Oh, sorry, minus 3 all over h. So compute this limit. So right here, you can see this is the problem we're going to be dealing with. So the first thing we're going to do is combine the 2 and the 1 right here, and that'll give us h plus 3 and minus 3. And so we're evaluating this from the left side. We're going to plug in the 0 once we cancel these out. And again, the h's cancel out, leaving a 1. So you see, you don't even really need to plug it in, as the limit will always be 1. And so right there, you see that these answers are both 1, which addresses the question in part F. Did your answers in part D and E equal the same number? If so, that's the derivative of f at 2. And so they did in fact equal each other. And so our derivative of f at 2 is 1. So use what you learned in parts B and C and this part to write down the derivative of f as a piecewise function. For example, if the derivative of f was 4x when x is less than 2, and x plus 4 when x is greater than 2, and no derivative at x equals 2, then f prime x equals this. So this is just an example in the notation. So as you can see right here, we have both equations. We take the derivative of this, so the 1 disappears, and using the power rule here, you get just 1. And then for this equation, you get f of x minus half, or f of x equals half, sorry, times x minus 1 squared plus 5/2. So basically what you're going to do here is the half is taken out, and then you have this squared. Once you bring that down, the half times 2 cancels out, gives you a 1. The 5/2 derivative of that is just 0. So after this power rule, that's going to leave you right here with just an x minus 1 for the right side of the function. And that is when x is greater than or equal to 2. So in this notation right here, you see this is the derivative of f of that piecewise function. When x is less than 2, it'll be 1. And when it's greater than or equal to 2, it will be x minus 1. And so you also can see that by plugging in the 2 here, 2 minus 1, that will give you the value of 1 for both parts of this piecewise function. So to answer this question, yes, they are the same. And the derivative of f at 2 equals 1. And this is the notation to write it in. So that is the end of my first demonstration. Thank you, and I hope you enjoyed it.